You think gravity is a pull, an invisible tug between objects. The Earth pulls the moon, the sun pulls the Earth, a black hole pulls everything. That picture feels obvious. It feels mechanical. Clean. Two masses, a force between them, end of story. But this is wrong. Gravity does not pull. At least, not in the way you imagine. When you drop a stone, you picture the Earth reaching up and dragging it down. A kind of cosmic magnetism, but nothing reaches. There is no invisible rope. The stone falls, because space-time itself is shaped in a particular way, and that statement probably feels vague, maybe even evasive. Good. Because the force picture is comfortable precisely because it hides what is actually happening in Newton's universe. Gravity is something objects do to each other. Mass creates force. Force causes motion. But in Einstein's universe, gravity is not something objects do. It is what space already is. Imagine you are inside an elevator in deep space. No windows, no stars, nothing to compare against. If the elevator accelerates upward, you feel pressed into the floor. Your body insists, gravity, but there is no planet beneath you, no mass pulling you down. The sensation is identical. That equivalence is not a trick. It is a clue. Acceleration and gravity are indistinguishable, which means gravity might not be a force at all. It might be geometry. Objects do not fall because they are pulled. They fall because they are following the straightest possible paths in a curved space-time. Straight paths can look curved if space itself is curved. This is not poetic language. It is literal. Remove the idea of force. Remove the idea of attraction. Replace it with shape. Mass does not reach out and grab other mass. Mass tells spacetime how to curve, and curved spacetime tells matter how to move. If that sounds abstract, it should, because once gravity stops being a force, something else changes too. If gravity is geometry, then extreme gravity is not stronger pulling. It is extreme curvature, and that is where black holes begin to stop being objects and start becoming something else entirely. You still imagine space as nothing, a backdrop, a void, a silent container where planets drift and stars burn. Even after accepting that gravity is geometry, you quietly keep this picture. Objects are real. Forces may be geometric, but space itself still empty. This is wrong. If gravity is curvature, then something must be curving, and nothing cannot curve. We speak casually about empty space, but empty space in general relativity is not an absence. It has structure. It has measurable properties. It stretches. It compresses. It ripples. When massive objects move, space does not remain indifferent. It reacts. When two black holes orbit one another, they send gravitational waves outward, ripples in spacetime itself. Those waves travel across billions of light-years and physically change distances as they pass. Not metaphorically, literally. Instruments like LIGO measured those distortions directly. Space moved. Nothing moved. That sentence should feel uncomfortable. You are used to thinking that movement requires things, particles, fields, something tangible. But spacetime is not a stage. It is part of the cast. Even in regions with no matter at all, spacetime can be curved. It can expand. It can carry energy in the form of gravitational waves, and this forces a shift that is easy to underestimate. If space can bend, then distance is not fixed. If space can stretch, then separation is not absolute. If space can ripple, then emptiness is dynamic. The idea of where becomes less solid. Consider the expanding universe. Galaxies are not flying outward through pre-existing emptiness. The emptiness itself is expanding between them. There is no external container. No outside into which the universe grows. Space is not inside anything. It is the thing. This is why the language of pulling becomes inadequate. When a massive star collapses, it is not merely drawing material inward through some invisible attraction. It is altering the geometry so severely that the structure of spacetime rearranges itself. But collapse is not just matter compressing, that is geometry changing character, and once you accept that space is physical, that it can be shaped, then you must also accept that it can be shaped so extremely that the idea of distance begins to fail. Black holes are not dense objects sitting in space. Are regions where the geometry of space has been warped beyond a threshold that is not about strength, but about structure. And once geometry crosses that threshold, something irreversible happens, not to matter first, but to space itself. You imagine a black hole forming like this. A massive star runs out of fuel. Gravity pulls inward. Matter compresses. Pressure rises. Everything gets squeezed smaller and smaller, until it becomes infinitely dense, a crushed sphere, a cosmic atom. That image is everywhere, and it is wrong. Not completely wrong, but wrong in the way that matters. Because collapse is not fundamentally about matter being squeezed like clay. It is about geometry losing its balance. When a star is alive, something subtle is happening. The outward push of radiation from nuclear fusion balances the inward curvature of spacetime caused by its mass. It is not simply pressure versus pull. Its geometry held in tension. Fusion stops. The outward support disappears. And the curvature wins. But what wins is not force. It is shape. As the star collapses, matter does not just move inward through space. Space itself is reconfiguring. Imagine drawing lines that represent the possible paths light can take near the star. As the collapse deepens, those light paths tilt inward, more and more. Not because something is dragging light, but because the geometry is tilting. Eventually, those paths tilt so severely that every possible future path points inward. Every one is the crucial shift. The story is no longer about crushing material into a smaller and smaller region. It is about the future itself. Narrowing. You can remove the mental image of a hard, dense sphere, replace it with a funnel in spacetime. Not a physical funnel you could touch, but a structure in which all forward directions converge. Even light, which normally defines what outward means, loses the ability to move away. And notice something unsettling. This description barely mentions matter, because at the extreme limit, matter becomes secondary. General relativity predicts that under sufficient collapse, curvature grows without bound. Not necessarily because matter is infinite in some mechanical sense, but because the geometry no longer admits stable paths outward. The word singularity gets introduced here. People imagine a tiny, infinitely dense point, but the singularity is not a solid object hiding at the center. It is a place where the mathematical description of spacetime breaks down. The equations stop, not because there is a hard nugget of material, but because geometry has become undefined. That is a very different kind of failure. So, when you think of a black hole forming, stop picturing matter being crushed into a smaller ball. Instead, picture the structure of spacetime narrowing until all possible futures collapse inward. Black holes are not primarily about density, they are about direction. And when direction itself becomes trapped, you are close to something new. You picture a black hole as a dark sphere, a boundary in space, a surface you could point to. Cross this line and you are trapped. It feels like a wall. Invisible, but real. This is wrong. The event horizon. It is not a material surface. It is not a membrane. It is not a shell surrounding something solid. It is a statement about the future. Imagine you are floating far from a collapsing star. You shine a flashlight outward. The light escapes easily. No resistance. As the collapse deepens, you repeat the experiment closer in. The beam still escapes, but its path bends more noticeably. Closer still. The beam struggles more. It curves sharply. But at a certain distance, something strange happens. You shine the light outward, and it never reaches distant space. Not because it hit something. Not because it slowed down, but because every possible outward path eventually curves back inward. The event horizon is defined precisely at that threshold. It is the location beyond which no future-directed path can reconnect with the outside universe. Notice the phrasing. Future-directed. The horizon is not about space alone. It is about spacetime. It does not block you like a wall blocks a ball. It rearranges what forward means. Inside the horizon. Moving toward the center is not a choice in the ordinary sense. It is as inevitable as moving toward tomorrow. You do not choose to travel into the future. You simply do. Inside a black hole, moving inward becomes as unavoidable as aging. That is not metaphor. In the mathematics of general relativity, the radial direction, what you think of as inward, becomes time-like. It takes on the role that time normally plays, and time-like directions cannot be avoided. You can choose where to step in space. You cannot choose not to move into the future. The event horizon marks the boundary, where inward motion becomes your future. This is why it cannot be a surface in the ordinary sense. Nothing locally dramatic happens as you cross it. No flash, no shock. In fact, if the black hole is large enough, you might not notice the crossing at all. That the horizon is not defined by what you feel. It is defined globally by whether light sent outward now can ever reach distant observers. To determine whether you are inside it, you would need to know the entire future of the universe. That should disturb you. A boundary that depends on the future is not a simple physical edge. It is a feature of the entire space-time structure. Black holes are not spheres sitting in space. They are regions where the geometry rearranges causality itself. And once causality bends far enough, escape stops being a possibility. Not because something holds you, but because the structure of can has changed. You still want black holes to be rare, special conditions, unusual stars, extreme accidents in an otherwise stable universe. It feels comforting to imagine that if things had been slightly different, they wouldn't exist. But once you accept gravity as geometry, that comfort starts to erode, because general relativity does not merely allow black holes. Under very ordinary assumptions, it predicts them. In the 1960s, mathematicians began asking a simple but ruthless question. If spacetime curves enough, What must happen? Not in special symmetrical cases. Not for perfectly smooth stars, but in messy, realistic collapse. The answer came in the form of what are now called the singularity theorems. Developed by people like Roger Penrose and Stephen Hawking, the theorems did not rely on detailed properties of matter. They relied on geometry. If enough mass energy is compressed into a region, if spacetime curves beyond a certain threshold, if causal paths tilt inward sufficiently, then the formation of a trapped region, an event horizon, is unavoidable. Unavoidable. Not because of the chemistry of stars. Not because of nuclear reactions, but because of the structure of the equations. The equations themselves insist on it. And this is where the intuition shifts again. Black holes are not rare because the universe sometimes gets violent. They are rare only because the conditions for extreme curvature are rare. But once those conditions are met, the result is not optional. It is as rigid as a geometric proof. If you draw certain shapes on a sphere, certain intersections must occur. If spacetime curves in certain ways, horizons must form. The inevitability is mathematical. That should unsettle you because it means black holes are not pathological. They are not glitches in the theory. They are the theory behaving honestly under stress. When gravity becomes strong enough, spacetime reorganizes itself into a configuration that includes a horizon. The horizon is not added. It emerges as the only consistent structure available. In that sense, black holes are not objects inserted into the universe. They are phases of geometry, like ice forming from water when temperature crosses a threshold. Below a certain curvature, spacetime behaves one way. Above it, it reorganizes. The fact that our universe contains massive stars simply ensures that the threshold will sometimes be crossed. But even without stars, the equations themselves contain black hole solutions. Empty space can curve into one. Geometry alone can sustain it. So the deeper reason black holes exist is not as strapachical. It is structural. The laws governing spacetime contain within them configurations where escape is impossible. And once you see that, a new discomfort appears. Because these laws, general relativity, are classical, smooth, continuous, deterministic, but the rest of physics is not. And if black holes are inevitable consequences of smooth spacetime, what happens when smoothness itself breaks? At this point, you might feel something close to stability. Black holes are geometric. They are inevitable. They emerge from the equations of general relativity, clean, logical, almost elegant, but there is a fracture running underneath this picture, because general relativity describes spacetime as smooth, infinitely divisible, perfectly continuous, curvature, defined at every point. Quantum mechanics does not allow that comfort. At very small scales, the universe is not smooth. It fluctuates, it jitters, fields refuse to stay quiet. And this is where the unease begins. Richard Feynman was deeply suspicious of any theory that pretended gravity could remain classical while everything else was quantum. Did not deny general relativity's success. He questioned its completeness. If matter is quantum and matter shapes spacetime, then spacetime must, in some sense, inherit quantum behavior. It cannot remain perfectly smooth while everything embedded within it flickers with uncertainty, but black holes push general relativity to its extreme. They require curvature that grows without bounda singularity, where the equations stop making sense. That stopping point is not just a technical inconvenience. It is a signal. General relativity predicts its own breakdown, and quantum mechanics becomes unavoidable exactly where curvature becomes infinite. You can ignore quantum effects when gravity is weak. You cannot ignore them when itself is compressed to its limit. So here is the tension. Black holes are inevitable in classical geometry, but classical geometry cannot survive inside them. The theory demands horizons. The theory also predicts its own failure at the center. That is not elegance. That is incompleteness. Feynman worried about this kind of inconsistency because physics does not tolerate partial truths forever. If black holes are honest expressions of gravity, then they are also places where our current understanding fractures. They exist because the equations insist. But at their core, the equations surrender, and that surrender is not philosophical, it is mathematical. So black holes are not just geometric inevitabilities, they are boundaries of knowledge, places where smooth spacetime ends not only physically, but theoretically. And that raises a final question. What does it mean for space itself to end? You imagine the universe as continuous, a seamless expanse, stretching forever, unbroken, a stage that holds everything. Black holes force you to abandon that comfort. Because inside a black hole, space itself can terminate. Not violently, not explosively, not like a tear or a rupture, simply. Spacetime ends. Imagine standing on a path that always leads forward. Normally you walk, you move, you progress. Time stretches ahead. space expands around you. Now imagine that path, narrowing, curving, tilting, until every direction forward points inward, and the very concept of outward disappears, until the path itself stops existing beyond a point. This is what the singularity represents. Not a point in space, not a dot in the cosmos, a place where space, the very fabric in which we exist, ceases to be defined. That is a horizon, and beyond it, the rules themselves dissolve. Causality rearranges. Distance loses meaning. Time merges with space in ways our intuition cannot follow. Black holes exist not because the universe fails, they exist because the universe is honest. They show what space-time must become when curvature reaches its logical extreme, and the philosophical awe emerges here. The universe allows space to end, not by destruction, not by collapse, but as the inevitable consequence of its own structure. Black holes are not errors, not exceptions, not accidents. They are truth made tangible, the geometry of inevitability. When you confront that, you realize the cosmos is stranger than we can imagine, and our intuition, built on empty space and pulling forces, fails utterly. Reality is not continuous. Reality is conditional. And somewhere, in every black hole, space itself bows out of existence. This is why they exist at all.